Okay, so today we're going to go over more advanced uses of the L'Hopital's rules, specifically those seen in Calculus BC. Now, I did this because this is my 50th video, and so I decided since we started with simple L'Hopital's rule, we might as well end the 50th with a more advanced form. So that's what we're going to do today. So as I said, this is a Calculus BC topic. You may be familiar with the AB form of L'Hopital's rule, that being if a function the limit of a function is either 0 over 0 or infinity over infinity, then you can take the derivative of both the numerator and the denominator, and you can find the limit that way. Now, that's the general use of L'Hopital's rule. However, L'Hopital's rule can be found, or it can be used on any indeterminate limit. However, the value can only be solved if the limit is in a quotient form. And so today we're going to go over separate types of indeterminate forms and how to employ the L'Hopital's rule using them. Okay, so this is of course the most basic form of an indeterminate limit. For instance, 0 over 0 or infinity over infinity is an indeterminate quotient limit. So if you want to find the value of a limit this way, well, it's quite simple. It's already in quotient form. All you have to do is state that the numerator is 0 or infinity, and the denominator is 0 or infinity. And from there, you can find the derivative of the numerator and the derivative of the denominator, find the limit of that function, of that fraction, and then there you have it, the value of the indeterminate quotient limit. Now, keep in mind that you're not taking the derivative of the actual fraction itself. You're just taking the derivative of the denominator over the derivative of the numerator over the derivative of the denominator. So this one is quite simple, and hopefully you're familiar. Now, here are what I like to call indeterminate product forms. They can either be represented as infinity times 0 or 0 times an undefined function, or plus or minus infinity times an undefined function. And this over here should be plus or minus as well. It doesn't really matter whether or the state of infinity, whether it's plus or minus, or positive or negative, I should say. So these are the three product indeterminate forms. Now, I'm going to represent the indeterminate product form that I'm about to show you with two separate variables. Let's say you're taking the limit as x approaches 0 of f of x times g of x. Now, let's say that f of 0 is infinity, and g of 0 is 0. Now, that would make this product indeterminate. And so to get into quotient rule, you're going to equate this to the limit as x approaches 0 of g of x over 1 over f of x. Now, this will still be, of course, indeterminate. However, it's now in quotient rule, and from here you can just find the derivative of the numerator and the derivative of the denominator. But you have to, of course, state that this quotient or this fraction is indeterminate. Okay, so we're nearing the end. There are only 4 indeterminate forms that I'm going to go over. This one is the difference indeterminate form. It can be represented by either infinity minus infinity or negative infinity plus infinity. So again, let me give you an example, a general example. Let's say we have the limit as x approaches infinity of f of x minus g of x. Well, in order to employ the L'Hopital's rule, you of course have to turn this into a fraction form. You can do this by either factoring out a common a common variable found in both of them, and then divide it. So let's say that both f of x and g of x featured x. Well, you could, of course, factor out the x, and of course, move it to the denominator, as I just said. If that doesn't work, you can then turn both f of x and g of x into fraction forms themselves, and then combine the two in a way. So let's say that f of x is 1 over, no, that won't work. 1 over x minus 1, and let's change this x to a 1, for example. And let's say g of x is 1 over natural log x, for example. Both of these would be indeterminate. And so if you'd like to find the value the true value, you could combine these into one fraction and end up with natural log x minus x minus 1 over the product of the two. And if you were to do this, then you can, of course, just find the derivative of the numerator, derivative of the denominator, state that it's indeterminate, and then find the true value of this function. So that's how you deal with difference indeterminate forms. So this is the last indeterminate form that I'm going to go over, and it involves powers and exponents. And it is absolutely BS. It doesn't make any sense. But you do have to understand, or you don't necessarily have to understand, you have to recognize that 1 to the power of infinity is indeterminate, 0 to the power of 0 is indeterminate, as well as infinity to the power of 0, which is indeterminate. So this is the most difficult to deal with, although it's the process in finding, or the process in using the L'Hopital's rule for indeterminate powers is quite methodical. Let's say that you have a limit as x approaches infinity of, I don't know, f of x to the power of 1 over g of x. Now let's say that f of infinity is infinity and g of infinity is infinity. That means that you truly have infinity to the power of 1 over infinity, which is actually infinity to the power of 0, which is indeterminate. So as I've said multiple times, in order to use L'Hopital's rule, you have to have an indeterminate fraction, or at least that's how you can employ it. That's how you use L'Hopital's rule. You can use it on any indeterminate function. However, it has to be in fraction form. And so we're going to change this to fraction form. What we're going to do is we're going to say that y is equal to f of x to the power of 1 over g of x. From here, we're going to take the natural log of both. So we'll have natural log y equals natural log f of x to the power of 1 over g of x, which is actually equal to 1 over g of x natural log f of x. Because when you take the natural log of something, you can, of course, move the exponent to the front of the natural log, as if you're multiplying it. So from here, we can take the limit of x as approaches infinity of natural log f of x over g of x. As soon as you find the value of that, you can raise it to the power of e, and you'll have your true value. And so that's all 4 indeterminate forms that I'm going to present today, the ones that are only seen in Calculus BC. And we're going to move on to the practice problem from here. Okay, this is practice problem 1. First, we have to check if this limit is indeed indeterminate. So the limit as x approaches 0 of 2 of x is equal to 0, of course. The limit as x approaches 0 of sine of x, or sorry, sine of 0, is also 0. And so this limit is, or sorry, this function is indeed indeterminate. So we're going to have to employ L'Hopital's rule. So we're going to say that since, oh god, this is going to take a while. Since the limit as x approaches 0 of 2 of x equals 0, and the limit as x approaches 2 of 0 of sine of x is 0, then the limit as x approaches 2 of x over sine of x is indeterminate. I'm just going to skip that part. Of course, you have to write it, but there are a lot of practice problems, so it's going to take too much time. You understand. So we're going to say that since this limit is indeterminate, and the limit as x approaches infinity, or sorry, x approaches 0 of 2 of x over sine of x is equal to the limit as x approaches 0 of the derivative of the numerator, which is 2, over the derivative of the denominator, which is cosine x. So from here, we can say that the limit as x approaches 0 of 2 over cosine x, x is equal to 2 over 1, which is equal to 2. So the true value of our limit as x approaches 0 of 2 of x over sine of x is equal to 2. Okay, this is practice problem 2. Now, as you can already tell, that this function that we have, this limit, is, if it is indeterminate, is most likely going to be in product form. So, of course, we have to first test if it is indeed indeterminate. So let's start off with the sine x over here. If we were to take the limit as x approaches 0 of sine 2x, we'd of course end up with 0. Now let's generalize cotangent a bit. Cotangent of 6 of x, or let's just go with cotangent of x, is equal to cosine x over sine x. Now cosine of x is equal to 0. Sorry, what am I saying? Cosine of 0 is equal to 1. And so this fraction over here, cotangent of x, is equal to 1 over sine of 0, which is 0. Now you can tell that cosine of 0 over sine of 0 is undefined, and therefore cotangent of 0 is undefined. And so we have the product of essentially a product consisting of an undefined value times 0. And of course, that's indeterminate. So what we're going to do is we're going to have to employ the L'Hopital's rule, of course, but first we have to get into fraction form. So we can do this by equating this to the limit as x approaches infinity, sorry, 0 of sine of x, sorry, sine of 2x over tangent 6x. And if you're wondering as to how I did this, it's because, well, cotangent is equal to 1 over tan. So we have 1 over tan 6x, sorry, 1 over tangent 6x times sine 2x. And from there, it's quite rudimentary to get, or it's quite elementary to get what I did. So the limit as x approaches 0 of sine 2x is 0. The limit as x approaches 0 of tangent 6x is also 0. And so we end up with 0 over 0. Now you have to put the proof on an exam, or you have to state the proof, but we can already tell that this is indeterminate. And so I'm just going to equate this to, the limit as x approaches 0 of 2 cosine 2x, as that's the derivative of the numerator, over the derivative of the denominator, which is 6 secant squared 6x. If you're curious as to how I got this, well, I've uploaded a video in the past going over all the derivatives, antiderivatives of trig and arc trig functions. So inverse trig functions. So if you're curious, just go ahead and watch that video. But from here, we still have to find this value. So the limit as x approaches 0 of 2 cosine 2x is equal to 2. And the limit as x approaches 0 of 6 squared 6x is equal to 1. So the limit as x approaches 0 of cotangent 6x sine of 2x is equal to 2. Okay, this is practice problem 4. The final one, in fact. We're told us to find the limit as x approaches infinity of e to the power of x plus 1, all to the power of 1 over x. So, per usual, we're going to check to see if this limit is in indeterminate form. And we can do so by just taking the limit. So, this is equal to e to the power of infinity, which is going to be infinity plus 1, still infinity, to the power of 1 over infinity, which is, of course, 0. So we end up with 0, infinity to the power of 0, which, if you'll recall, is indeed indeterminate. So we can now employ L'Hopital's rule, but first we have to get this fraction into indeterminate form. So, fraction form. So we're going to say that e to the power of x plus 1 is equal to y. And from here, we can just take the natural log of both sides. So we end up with natural log y equals 1 over x, natural log e to the power of x plus 1. And now we can take the limit of this. So we can say that the limit of x as it approaches infinity of natural log e to the power of x plus 1 over 1 to the power of 1 over x is indeterminate. Now I'm going to simplify this quite a bit. Instead of 1 over x, I'm just going to simplify that to x. So as you can see, if we were to take the limit of the numerator, the limit as x approaches infinity of natural log e to the power of x plus 1, we'd end up with natural log e to the power of infinity plus 1, which is natural log infinity plus 1, which is natural log infinity, which is infinity. So the numerator is infinity, and the denominator is in fact infinity as well. Now this is obviously indeterminate, meaning that we can take the derivative of the numerator and the denominator. So the limit we currently have is equal to the limit as x approaches infinity of the derivative of the numerator, which is going to be e to the power of x, over e to the power of x plus 1. That is the derivative of natural log e to the power of x, all over the derivative of x, which is 1. So we currently have, I can simplify this by merely taking out the denominator
is the limit as x approaches infinity of e to the power of x over e to the power of x plus 1. Now, the issue here is that we can take the derivative of both the numerator and the denominator as much as we want. It doesn't matter. It's always going to be equal to e to the power of x. So we end up really with just 1, if this makes any sort of sense. Keep in mind that if you have polynomials or exponentials with similar or with exponents that are exactly the same, then you have to take the ratio of the constants, which is going to be 1 in this case. So we end up with limit as x approaches infinity of essentially 1. Now keep in mind that this is what natural log y is equal to. Natural log y is equal to 1. So what we're going to do is we're going to raise both sides by e, and we end up with y equals e. That is basically it for this video. If you have any suggestions for future videos, please put them in the comments below. And thank you for watching this far. Okay, this is practice problem 3, the second to last practice problem. Now this is going to involve indeterminate differences. So let's of course prove that this is indeterminate. We're going to take the limit as x approaching infinity of x times e to the power of 1 over x minus x. So in reality, this is equal to infinity times e to the power of 0 minus infinity, also known as infinity minus infinity, and that is of course indeterminate. So we're going to attempt to get this indeterminate limit into quotient form. The first thing we're going to do is we're going to factor out the x. So we can say that this limit is equal to the limit as x approaches infinity of x times e to the power of 1 over x minus 1, at which point we can divide by 1 over x. So this is going to be equal to the limit as x approaches infinity of e to the power of 1 over x minus 1 over x. Now from here, we're going to determine if this limit, this quotient fraction is indeed indeterminate. So this over here, we can take the limit of the numerator, the limit as x approaches infinity of e to the power of 1 over x minus 1, which is equal to e to the power of 1 over infinity minus 1, which is equal to 1, which is equal to e to the power of 0 over 1. Now, e to the power of 0 is, of course, 1, because anything to the power of 0 is 1, with the exception of infinity. So we end up with 1 minus 1, which is equal to 0, meaning that the numerator is equal to 0, over the limit of the denominator, which is the limit as x approaches infinity, 1 over x, which is 1 over infinity, which is 0. So our limit is indeterminate. And so, of course, you're going to have to naturally state all the proof and how this limit is indeterminate. But since I just proved it to you, I don't really want to write it all down, and I think what I've done is adequate. So we're going to find the limit of the derivative of the numerator and the derivative of the denominator. So we're going to state that this limit is equal to the limit as x approaches infinity of the derivative of the numerator, which is equal to, okay, so sorry about that break. I had to actually do the derivative by hand because I blanked out for a moment. I don't know why. I mean, the derivative of e to the power of 1 over x is equal to negative 1, or so, yeah, we might as well go with that, negative 1 over x squared times e to the power of 1 over x, because e to the power of f of x, for instance, is just equal to f prime of x times e to the power of f of x. So I don't really know why I blanked out, but this is the derivative. So let's go with that. Now we have to find the derivative of the denominator, which is 1 over x. Now, the denominator is 1 over x. The derivative is negative 1 over x squared. And so you may notice a similar term in both the numerator and the denominator, that term being negative 1 over x squared. So we can cross this out. We can say that the limit that we currently have is equal to the limit as x approaches infinity of e to the power of 1 over x. Now, I think we've gone over this multiple times. That's equal to e to the power of 1 over infinity, which is e to the power of 0, which is 1. So the final answer is 1. So now we're going to move on to practice problem 4.